Far beyond the Milky Way, a single point of light hides a black hole so huge it could swallow billions of suns, the quasar S5014 or Night 1. Tonight's episode drifts slowly inward from the cosmic web to the very edge of its event horizon, in a calm, sleep-friendly journey through deep time and gravity. If you enjoy relaxing to long cosmic documentaries like this, please like the video, subscribe and turn on the bell so you never miss a night among the stars. S5, 0014+81, shines in the constellation Cepheus as a hyperluminous quasar powered by a black hole of tens of billions of suns. That single fact already carries quiet weight, because it shows that nature can assemble engines far beyond anything familiar from the Milky Way. By the end of this journey, the structure, feeding and limits of this ultramassive black hole will feel clear and gently ordered in the mind. Its light travels for more than 12 billion years before reaching modern telescopes. It turns a tiny patch of northern sky into a distant patient storm of energy. In the language of astronomy, S5 0014+81 is a quasar, meaning its central black hole glows by heating falling gas into hot plasma. The core idea stays simple. Gravity pulls matter inward, and the loss of height in the gravitational field reappears as light. Around the centre sits a black hole, as heavy as tens of billions of suns, wrapped in a thick whirling structure of gas and radiation. The full system behaves like a remote lighthouse in gentle cosmic fog, sweeping out power from radio waves up to X-rays. This object belongs to a time when the universe is still young, yet some black holes already stand among the largest that theory allows. That early growth matters because it tests how quickly small black hole seeds can gain mass in the crowded gas-rich young cosmos. If a quasar this bright shines so early, then the flow of gas, the pattern of mergers and the pull of gravity must all cooperate efficiently. The quasar becomes a natural laboratory written into space-time, offering a long record of light that encodes the behavior of its surroundings. Each photon that arrives at a telescope tonight began its journey when galaxies were still assembling their first extended generations of stars. In a quiet way, every tiny point of light from S5014+81 is an old message about growth, heat and structure in the universe. The mass of the black hole sits at one extreme, while the age of the light rests at another. Together they turn this distant source into a gentle marker of just how stretched cosmic scales can become. The tiny area of sky occupied by this beacon adds a third extreme, reminding the listener how much detail can hide in a narrow field. The quasar can be pictured as a single bright ember in the wide weave of the cosmic web. It glows steadily, while matter streams inward along unseen strands. This image matters because it links huge scales from diffuse intergalactic gas to the intense brilliance of the region just outside the event horizon. It shows that no part of the structure lives alone, and that every shining zone is nourished by softer, more spread-out surroundings. In the background of this picture stands the idea of redshift, a measure of how much the universe has expanded while the light is in flight. A high redshift means the light has travelled for a very long time, and that the cosmos was much younger when the photon set out. For S5, says +1, that journey covers most of cosmic history, so each photon acts as a gentle witness to changing conditions in deep time. From a practical point of view, the quasar also matters because its unusual brightness makes it easier to study than many fainter objects at similar distance. From a practical point of view, the quasar also matters because its unusual brightness makes it easier to study than many fainter objects at similar distance. Those measurements break the light into a spectrum. The resulting pattern shows how gas moves, how hot it becomes, and how close it can orbit before the black hole draws it inward. In that way, an initially dry catalogue entry turns into a concrete probe of both gravity and galaxy formation in the early universe. The key idea of this opening section is that S0014+81 is not only big and bright, it also sits at a special moment in time and distance. Its existence suggests that black holes can grow very rapidly under the right conditions, or perhaps that they begin from seeds more massive than once assumed. Either option offers important constraints, helping theorists decide which growth models are gentle sketches and which can stand beside precise data. At the same time, the quasar lies so far away that it never touches daily concerns, remaining a silent landmark rather than any source of danger. At the same time, the quasar lies so far away that it never touches daily concerns, remaining a silent landmark rather than any source of danger. Across the coming sections, the focus will move gradually from the largest environment around S50014+81 down toward the last stable orbits near its black hole. That descent in scale is designed to feel like a slow, stable journey, rather than a sudden plunge into something harsh or threatening. Along the way, each layer of gas, dust and light will take time on stage with simple explanations and repeated reminders of why that layer matters. The goal is gentle understanding. The story shows how this single quasar fits into cosmic history, and how its extreme heart still obeys calm physical laws. With that promise set, the narrative is ready to step outward. It will look at the surrounding cosmic web that quietly channels matter toward S500+81 over eons. Far beyond the bright point of S500+81, the universe stretches into a vast pattern of structure called the cosmic web. In this web, matter does not spread evenly, but gathers along long filaments like slow rivers of gas and dark matter, crossing a wide plain. The essential idea is gentle but powerful. Enormous black holes need more than local fuel and depend on a grand network that feeds entire regions over billions of years. Without the web, S500+81 would shine less fiercely, because its surroundings would hold less material ready to drift inward. The cosmic web forms as gravity amplifies tiny variations in the early universe. Slightly denser regions pull a little more strongly, drawing in gas and dark matter, and those regions grow over time. Vast empty zones become quieter gaps, while connected filaments turn into extended channels, where galaxies and quasars eventually settle. Each filament is not a rigid bridge, but a soft flowing structure, with gas that moves slowly toward deep gravitational wells. In that setting, S500+81 is not an isolated beacon, but part of a larger environment shaped by these filaments. The quasar's host halo sits near a junction where several strands likely meet a quiet crossroads, where matter arrives from multiple directions. This crossing point matters because the more paths that converge, the more steadily gas can be supplied to the central regions over very long periods. Astronomers sometimes describe these intersections as nodes in the web, where clusters and massive galaxies prefer to form. In one of those distant nodes, hidden by time and distance, the halo of S50014+81 gathers its resources. The gas that travels along the filaments does not rush like a storm. It moves at cosmic walking pace, guided mainly by gravity, cooling gently as it approaches denser zones. On its way inward, it may shock, compress, or fragment into clumps that later form stars, but the broad trend remains one of slow infall. This slow continual motion provides a natural way for a black hole to gain mass without exhausting its surroundings too quickly. The calm flow contrasts with the intense brightness at the center, like a quiet network of canals feeding a glowing harbor. Visualizing the web also helps explain why such an extreme quasar appears in a young universe. filaments act early gathering material long before galaxies are fully mature. Because the network spans large distances, it can funnel gas into forming halos even when the cosmic clock is still in its early hours. That early supply allows seeds of black holes to start growing before much time has passed. Over hundreds of millions of years, this steady feeding can raise a central object from modest size to something far more massive. In that sense, the web gives the black hole both a starting advantage and a long, slow diet. The picture remains simple at heart. Large-scale structure sets the stage, and within that stage a few regions become particularly favoured for rapid growth. S5 0014+81 likely inhabits such a favoured spot. Its brightness hints that the local web has done its work well, delivering enough gas to keep the quasar active at a remarkable level. At the same time, the surrounding filaments and nodes stay invisible to direct vision, revealed instead through simulations and indirect observations of distant galaxies. They form a quiet scaffold that supports everything else in the story. Within that scaffold, every galaxy group and cluster finds an appropriate place, like beads arranged along softly curving strings. The surrounding web also hosts gas that never quite reaches the central halo, drifting in long arcs that may only slowly change direction. Those distant reserves widen the sense of scale, showing that the immediate fuel near the black hole is only a small part of the full system. Over time, small changes in density and temperature can redirect new streams of gas toward the halo, like subtle adjustments in faint faraway currents. In this way, the environment has both stability and gentle flexibility, allowing long phases of quasar activity followed by quieter intervals. From the perspective of a distant observer, the cosmic web around S5 remains an abstract idea. However, knowing that it exists gives a calmer sense of order. The quasar no longer seems like an impossible accident, but rather like a strong flame at the meeting point of long, faint streams of fuel. The image of pale filaments stretching across space can rest gently in the mind. Those strands connect the quasar to regions far beyond its own host galaxy. They also connect this single object to a wider pattern that includes clusters, groups, and eventually the large-scale map of the observable universe. With this layer in view, the next step inward feels natural. Attention can move from the cosmic web to the deep gravitational well that forms inside one of its nodes. In that well, a massive halo takes shape and prepares the ground for the growing black hole at the heart of S5 Deep inside, the cosmic web gravity shapes a region around S5 into a massive dark matter halo. The key idea is simple and steady. This halo acts as a deep gravitational well that gathers and holds gas stars and galaxies over long stretches of time. Without such a well, the quasar's black hole could not collect enough material to grow to tens of billions of solar masses. Dark matter forms the backbone of this halo, even though it does not shine or interact with light. It reveals itself only through gravity curving the paths of visible matter and guiding the motion of gas and stars. The halo stretches far beyond any luminous structure, much wider than the bright central quasar and its unseen host galaxy. In a quiet image, the halo can be imagined as a broad invisible valley in space-time, with all nearby matter gently sliding toward its center. This valley matters because it sets the overall depth of the gravitational environment around S5 The deeper the valley, the easier it becomes for the region to hold onto gas against internal winds, supernova explosions, or past quasar outbursts. Over cosmic time, the halo slowly grows as smaller structures fall inward and merge. These mergers bring in fresh, dark matter, and also deliver new gas-cold clouds and entire galaxies. Each event adds another layer to the halo's mass, and another step in the long history of building a home for the central black hole. The process does not look violent from this soft, distant perspective. It appears instead as a gradual thickening of the gravitational well, a deepening basin that becomes more and more effective at collecting matter. Close to the center of the halo, ordinary matter behaves differently from dark matter. Gas can cool, radiate energy, and sink deeper into the potential well. Dark matter does not cool in this way and stays more extended. This quiet separation leads to a simple structure. Dark matter forms a wide, diffuse envelope while gas settles toward the inner regions where a galaxy and its black hole eventually grow. The halo's gravity also shapes the motions of satellite galaxies and loose clouds that orbit within it. Their paths twist and curve, tracing out the depth of the invisible potential. Some satellites may be torn apart, leaving streams of stars and gas that curve around the center like very slow, pale ribbons. Over long time scales, these streams feed the inner regions and increase the mass available for the central engine. The importance of the halo becomes clearer when thinking about how bright S5014+81 appears. A quasar that outshines thousands of Milky Way galaxies combined needs a correspondingly massive reservoir of material. The halo provides that reservoir by anchoring the local cosmic web and holding on to inflowing gas. In this way, the halo links large-scale flows to small-scale accretion. It turns distant filaments into practical fuel lines for the black hole. Observationally, the halo leaves its signature in several gentle ways. It affects the speeds of stars and gas near the center and influences the distribution of galaxies in the surrounding region. At great distances, it can bend the paths of background light through gravitational lensing, slightly distorting the shapes of more remote galaxies. For a quasar at this redshift, these signatures may be subtle, but they remain part of the calm physical picture. The central black hole does not float alone in space. It sits at the bottom of a shared well that also contains a massive galaxy, smaller companions, and diffuse gas. This shared environment allows feedback from the quasar to travel outward, while inflows from the web continue to move inward. The halo mediates these exchanges by setting how strongly matter is bound to the region. If the well is deep enough, even powerful outflows cannot completely empty it of gas. They may heat or rearrange the material, but much of it remains available for future cycles of activity. Over time, a balance forms between inflow and outflow, between cooling gas and heated plasma. The dark matter halo does not change quickly in response to these smaller events. It remains a stable frame in which the faster, brighter processes unfold. That stability matters for the long growth of the central black hole. It ensures that the setting around S5014+81 does not shift chaotically from one moment to the next. Instead, the halo provides a slowly evolving stage on which the more rapid drama of accretion and feedback can play out. This calm backdrop fits the tone of the story. Even in the presence of extreme luminosity and enormous mass, the underlying structure behaves in a smooth, predictable way. With the halo in place, it becomes easier to understand how a giant galaxy can settle within it, and how gas can find its way toward the central regions. The narrative can now move gently inward again from the broad gravitational well to the luminous host galaxy that grows inside it and shares the same deep invisible valley. Inside the vast dark matter halo around S5014+81, a giant host galaxy slowly takes shape, resting like a bright island at the bottom of the gravitational well. The central idea is gentle and clear. This galaxy gathers stars, gas and dust into a single growing structure that shares its life with the ultramassive black hole at the core. Without such a galaxy, the quasar would lack both a stable setting and a long-term source of fuel. Astronomers often picture the hosts of powerful quasars as massive elliptical galaxies. That term simply means that their stars form a rounded, smooth distribution rather than a thin spiral disk. In the case of S5 or +81, direct images of the host are difficult because the quasar outshines the surrounding starlight by a large margin. Even so, theory and indirect clues suggest a very heavy galaxy, rich in old and intermediate-age stars. In a calm mental image, the galaxy appears as a soft, hazy glow wrapped around the blazing point of the quasar with its own quieter light, almost lost in the glare. Within that glow live billions of stars, each following its steady orbit in the common gravitational field. Each generation of stars enriches the gas with heavier elements when it reaches the end of its life. Over long stretches of time, this enrichment changes the character of the galaxy's gas and dust. The material that later drifts toward the central black hole carries traces of that history, including elements forged in earlier stellar cores. In this way, even a simple beam of light from S5 0014+81 encodes a story of cycles where stars form, burn and return material to the shared reservoir. The host galaxy does more than supply matter. It also shapes how the quasar looks from far away. Dust-lane star-forming regions and older stellar populations all contribute to how different wavelengths are absorbed or scattered. In some directions, thick dust may partially shield the central engine, softening the observed light. In other directions, clearer paths allow the full glare of the accretion disk and jets to escape. This uneven structure makes each line of sight a little different, even though the underlying system stays the same. The galaxy also contains a bulge of stars near the center, a rounded distribution that extends out from the black hole over many light years. This bulge matters because there is a quiet correlation between its mass and the mass of the central black hole in many galaxies. For S5 0014+81, that relation is stretched toward one extreme. The central object has grown to a truly extraordinary size, and the host galaxy must be correspondingly massive to provide a natural context. That shared growth hints at a long period of interaction between the black hole and its surroundings. At earlier times, bursts of quasar activity may have pushed gas out of the central region, slowing star formation for a while. Later, fresh inflows from the halo and the cosmic web may have brought new gas inward, restarting the cycle. Through all of this, the main body of the galaxy remains in place, acting as a long-lived container for matter and a stable reference frame for the orbits of stars. In one direction, the galaxy gradually blends into the wider halo and the surrounding filaments. In the other direction, it narrows into dense central regions where gas flows become more focused and the influence of the black hole becomes stronger. That smooth transition allows the narrative to slide gently from global structure to local detail. Thinking of the host as a city of stars can be helpful, as long as the image stays calm. The black hole occupies the bright central district while the rest of the galaxy stretches out like quiet neighborhoods and distant suburbs. Light from these regions reaches observers along with the quasar's glare, adding a faint collective background to the spectrum. This mixed light lets astronomers estimate how many stars are present and how old they might be even when individual stars cannot be resolved. Subtle imprints in the spectrum reveal absorption features from stellar atmospheres and diffuse gas. The important point is that the black hole does not act alone. Its enormous mass and brightness sit within a wider, slowly evolving companion made of stars and gas. Both components share the same deep gravitational well and influence each other over time. The galaxy channels gas toward the center and receives energy and momentum from the quasar in return. This quiet partnership sets the stage for more detailed structures closer in where gas becomes hotter, denser, and more directly tied to the black hole's pull. With the host galaxy now outlined in gentle strokes, the story can move inward again toward the extended halo of gas known as the circumgalactic medium that surrounds this distant system. The giant host galaxy of S5 0014+81 does not end where its last bright stars fade from view. Around it stretches a vast faint envelope of gas called the circumgalactic medium. The circumgalactic medium, or CGM, is the diffuse gas that surrounds a galaxy well beyond its visible edge. It forms a quiet boundary zone between the inner galaxy and the wider cosmic web. This hazy region acts as a long-term reservoir of fuel and memory for the system. Within the CGM, gas drifts, cools, and sometimes heats again under the influence of gravity and feedback. It holds material that once belonged to the galaxy, and material that has never yet crossed the bright stellar body. The CGM does not glow like a sharp shell. Instead, it resembles a soft extended mist that fills much of the halo around S50 plus Kyoskutnan. Some of this gas arrives along filaments that feed the dark matter halo. As the gas approaches the galaxy, it can slow compress and settle into the circumgalactic region before moving further inward. In other places, the CGM contains gas that has been pushed outward by earlier bursts of quasar activity or intense star formation. Outflows carry heated material into the halo, where it may eventually cool and begin to fall back. This cycle makes the CGM a gentle crossroads between inflow and outflow, between fresh fuel and recycled matter. Astronomers infer the properties of the CGM mainly through absorption lines in the light of background sources. When the light from a more distant object passes through the halo of S5, 0014+81 atoms in the gas absorb specific wavelengths. These narrow dips in the spectrum reveal the presence of elements like hydrogen, oxygen, and carbon. The exact pattern of absorption hints at temperature, density, and motion in the diffuse medium. For S5 0014+81, such observations are challenging but still provide a calm, indirect view of the gaseous cocoon around the host galaxy. The CGM matters deeply for the growth of the central black hole. Gas in this region sits close enough to be captured, yet far enough to remain in reserve for long periods. Over time, cooling patches of the CGM may form denser clouds. These clouds can drift inward under gravity feeding the inner galaxy, and eventually the accretion flows around the black hole. In this way, the circumgalactic medium acts like a broad, slow-moving pantry of matter, always present in the background. The same region also responds to the energy output of the quasar. Powerful radiation and fast outflows from near the black hole can heat parts of the CGM. Heated gas may rise in the halo and remain suspended there for long intervals before cooling again. This gentle feedback loop slows the rate at which fresh material reaches the center. It helps regulate the brightness of the quasar over cosmic time without shutting it off completely. The balance between cooling inflows and heated outflows shapes the structure of the CGM. In some zones, the gas remains hot and tenuous. In others, cooler clouds form moving along complex paths through the halo. The result is a multi-phase medium with different temperatures and densities coexisting in the same broad region. Even though this complexity is real, it can be held in a simple picture. The CGM behaves like a layered breathing halo of gas around the galaxy of S5 00+81. It receives matter from the cosmic web, stores it for a while, and then passes some of it inward. It also receives energy from the quasar and star-forming regions, distributes that energy outward, and slowly radiates it away. Through these processes, the circumgalactic medium links the vast scales of the halo to the smaller scales of the galaxy. It prepares the conditions for gas to cross the next boundary, where the medium becomes truly interstellar. In that inner region, gravity, pressure, and cooling act together to reshape the gently drifting circumgalactic gas into more compact structures. Some parcels of gas become part of extended fountains, rising, cooling, and falling in long arcs that trace the halo's quiet breathing. Other parcels follow straighter paths, sliding down the gravitational slope with fewer interruptions and arriving closer to the galactic disk. Over millions of years, these motions create subtle patterns in temperature and composition that future observations may be able to uncover. Each pattern adds another small clue to how efficiently matter moves from the web through the CGM and into central regions. In this sense, the circumgalactic medium quietly keeps track of the long dialogue between inflowing gas and energy flowing outward. That dialogue prepares the scene for the denser, more structured interstellar medium closer to the galaxy's heart. Inside the bright body of the host galaxy of S5 0014+81, gas becomes denser and more structured, forming what astronomers call the interstellar medium. The interstellar medium, or ISM, is the gas and dust that fill the space between stars inside a galaxy. It provides the immediate raw material for new stars and, more quietly, for the accretion flows that later reach the central black hole. In simple terms, the ISM is the inner circulation system of the galaxy, gently moving matter from place to place. This region matters because it turns the broad, diffuse supply of the circumgalactic medium into colder clouds and warm streams that can actually drift toward the core. Within the ISM, gas exists in several phases that differ in temperature and density. Cold molecular clouds gather in knots where gravity and cooling cooperate, while warmer, more diffuse gas fills much of the remaining volume. Hot bubbles may form around clusters of massive stars and supernova remnants. Though complex in detail, the broad picture stays serene. The interstellar medium behaves like a layered, slowly shifting fog threaded with denser patches. These patches are the birthplaces of stars and future contributors to the galaxy's central fuel. In the distant galaxy hosting S5 0014+81, the ISM likely remains rich and active. The universe is still young at the quasar's redshift, so gas fractions are high, and star formation can proceed vigorously. Each massive star that forms from the coldest clouds lives quickly and ends in an energetic explosion. Those explosions stir and heat the surrounding gas, sending shock waves that carve cavities and compress nearby regions. Over millions of years, this gentle agitation creates a textured pattern of bubble shells and filaments. In some places, gas becomes too hot and diffuse to sink further toward the center for a while. In other places, compressed clouds grow denser, cool more efficiently, and begin sliding inward along gradually curving paths. These quiet channels become hidden routes that guide matter from the outskirts of the galaxy toward its inner regions. Dust grains mixed into the ISM play a subtle role. They absorb and scatter ultraviolet and optical light, dimming the glow of young stars and changing the apparent colors of the galaxy. They also help gas cool by providing surfaces where molecules can form. In the host of S5 0014+81, dust may gather in lanes and patches that partially veil the central regions from some angles. When viewed along certain lines of sight, these dusty structures can soften the direct glare of the quasar, replacing it with a more filtered radiance. The same dust that hides starlight also traces the paths where gas is dense enough to approach the galactic center. Over time, gravity and pressure gradients coax parts of the ISM into slowly spiraling motion. Gas clouds follow orbits that are not perfectly closed. They gradually lose energy through radiation and interactions, allowing their paths to decay inward. This settling motion is not a single smooth flow, but a combination of many small steps. Clouds may fall toward the center, break apart, form stars, or be disrupted by feedback, then leave behind fragments that continue the journey. Each step is modest, yet together they produce a radial drift of material toward the inner kiloparsecs of the galaxy. In that inner region, the ISM becomes denser overall. Bars, spiral structures, or other gravitational features can further focus gas toward the very central zones. Even if the host galaxy of S5 0014+81 is more elliptical than spiral asymmetries, and past mergers can create non-circular motions. These motions act like gentle conveyors slowly moving gas into a compact central reservoir. From there, some fraction of the gas may feed circumnuclear rings or disks where star formation proceeds rapidly. Another fraction will eventually lose enough angular momentum to move closer to the black hole itself. The important idea is that the interstellar medium provides the last large-scale step in the inward journey. It turns the long-distance supply channels of the cosmic web and circumgalactic medium into concrete streams of gas within the galaxy. It also shapes how the quasar appears by adding dust obscuration and emission from star-forming regions around it. Light from S5 0014+81 carries imprints of both the bright nucleus and the layered ISM that surrounds it. For a distant observer, these contributions merge into a single spectrum. Within that combined light, careful analysis can separate broad features from the nucleus and narrower signatures from interstellar gas. The existence of strong emission and absorption lines in the spectrum reminds researchers that the black hole is embedded in a living medium not isolated in empty space. With this understanding, the focus can move one step closer to the center, where dust and gas in the innermost regions form thicker structures. These inner structures begin to limit direct lines of sight to the black hole and shape the specific windows through which the quasar can be studied. Inside the inner regions of the host galaxy of S5, 0081 dust gathers into lanes, clouds, and veils that lie between the bright nucleus and open space. Dust in this context means tiny solid grains mixed with gas made of heavier elements that earlier generations of stars have produced and released. The key idea is that this dust does not simply decorate the galaxy, but quietly shapes what light escapes and what remains hidden. It blocks and scatters ultraviolet and optical photons while allowing longer wavelength radiation such as infrared and radio waves to pass more easily. Because of this, the same quasar can look very different depending on the kind of light used to observe it. In visible light, thick dust can turn the central regions into a muted, reddened glow. In infrared, those same regions may shine more clearly warmed by the energy of the hidden core. In X-rays, dust has less control, and gas along the line of sight plays a stronger role. All of these effects combine to create what can be called observation windows, gentle openings in the complex fog between the black hole and distant telescopes. Some windows open wide at certain wavelengths and nearly close at others. The result is a layered view where each band of light tells a slightly different story about the same object. Dust lanes near the center of the galaxy may twist like soft dark ribbons across starlight when seen from the side. In some orientations, they partly cover the accretion region and broad line clouds around the black hole. In others, they leave a more direct path where high-energy radiation can escape with fewer obstacles. This geometry matters because it helps explain why some quasars appear strongly obscured and others look almost bare even when their central engines behave in similar ways. For S5 0014+81, the enormous brightness of the nucleus can overpower many dusty structures, yet even here obscuration plays a role. Certain lines of sight may be heavily dimmed, changing the observed color and apparent strength of emission features. Other paths align with clearer corridors carved by outflows or past episodes of activity. Infrared telescopes are especially helpful in peering through these dusty veils. Dust absorbs high-energy photons and re-emits their energy as longer wavelength infrared light. From afar, this reprocessed glow appears as a soft, warm background around the quasar. It reveals where dust is heated and how far the central influence extends into the surrounding gas. Radio observations can go even further through the fog. They capture emission from jets and extended plasma that dust barely affects at all. In that band, the quasar's structure stretches along narrow beams that run outward from the core, cutting through the obscuring material and carrying information about magnetic fields and particle acceleration. The presence of dust, therefore, does not simply hide the quasar. It redistributes energy and filters the view, turning different observational bands into complementary perspectives rather than rivals. Each perspective helps reconstruct a fuller picture of the environment around the ultramassive black hole. The interplay of dust, gas, and radiation also affects how the quasar interacts with its host galaxy. When dust absorbs energetic photons, it warms the surrounding gas and contributes to gentle pressure that can push material outward. In dense regions, this pressure may help clear small channels, while in others it may compress gas and encourage new star formation. Over time, these effects can subtly reshape the interstellar medium near the core. They change where cold clouds can survive and where they disperse. In the distant past of S5, 0014+81 cycles of activity likely created alternating phases of heavy obscuration and clearer views. During more obscured phases, much of the quasar's energy left the system in infrared and sub-millimeter light. During clearer phases, a larger fraction emerged directly in ultraviolet and optical bands. From the perspective of modern observers, this history is folded together into the current structure of dust and gas. Even though only one moment is visible at any given time, that moment carries traces of many earlier cycles. The calm lesson in this layer is that dust, often treated as an obstacle, also acts as a guide. It points to regions of dense gas traces past outflows and highlights places where the central energy has been absorbed and re-emitted. For S5 0014+81, these dusty structures define which paths of light reach the cosmos and which remain turned inward. Seen as a whole, the dusty core and its filtered light resemble a distant lantern wrapped in many thin shades, each one tuned to a different color. As the point of view shifts across wavelengths, those shades appear to lift one by one, revealing new patterns without disturbing the underlying calm of the central glow. With this understanding, the narrative can move closer to the immediate surroundings of the black hole, where fast-moving gas clouds in the broadline region respond directly to changes in the central radiation field, closer to the heart of S5. 0014+81 gas no longer drifts as calm clouds in the wider galaxy. It gathers into a compact bright zone where gravity is stronger and motions become much faster. This is the region that produces the broad spectral lines seen in the quasar's light. The broadline region is fast gas close to the black hole. Its importance is simple. The motions of this gas reveal how massive the central object must be, and the timing of its response to changes in brightness reveals how large this inner zone is. Together, those clues turn a distant point of light into a softly measured structure. In the broadline region, individual gas clouds orbit the black hole at thousands of kilometers per second. Their speeds are too high for any direct image, but their effect on light is quiet and clear. As each cloud moves the spectral lines, it emits shift slightly in wavelength because of the Doppler effect. Some clouds move toward the observer, some away, some across the line of sight. When their light blends, the result is a wide smeared feature rather than a narrow sharp line. That width carries the imprint of the velocity field around the black hole, In a gentle mental picture, the region resembles a glowing swarm of tiny lanterns moving along curved paths in a deep gravitational well. The swarm cannot be seen directly, yet its collective motion leaves a smooth, broad mark on the spectrum. For S5 0014+81, these broad lines are especially striking because they arise in the intense radiation field of an ultramassive black hole. The gas endures strong illumination and deep gravity at the same time. Light from the accretion disk shines outward and ionizes the atoms in the clouds. When electrons recombine or drop to lower energy levels, they emit photons at specific wavelengths. Those photons form the emission lines that astronomers study. The way the lines brighten or fade over time brings another layer of information. Changes in the central continuum light travel outward at a finite speed. Gas clouds at different distances respond with a delay. The delay between a change in the inner light and the response in a particular line encodes the light travel time. From that delay, the characteristic radius of the broad line region can be estimated. This method is often called reverberation mapping, a phrase that suggests echoes in a large hall. In the peaceful setting of this narrative, the idea becomes an image of soft ripples of light, moving outward from the center, gently touching the orbiting clouds in turn. Each cloud hears the change with a slight pause that depends on its distance. Observers far away only see the combined effect but can still decode the pattern. For an object as luminous as SV0014+81, the broad line region likely stretches across light weeks or light months, scaled up by the enormous mass of the black hole. Its gas must be dense enough to remain clumpy, yet extended enough to surround the core like a thick, glowing shell. The simple balance is this. Too close to the black hole, gas would spiral inward too quickly. Too far away, the radiation field would weaken, and the lines would change character. The region that remains between these limits becomes a stable if dynamic layer. In that layer, gravity sets the orbital speeds and radiation sets the temperature and ionization state. Together, these influences produce the smooth, wide features in the spectrum that give the region its name. The broad line region also helps connect observations of S5 0014+81 to quieter galaxies closer to home. In many systems, the relationship between line widths, time delays, and luminosity appears to follow gentle trends. These trends allow approximate black hole masses to be estimated even when full timing data are not available. For this quasar, the extreme mass derived from such methods has placed it among the heaviest known black holes. The broad line region therefore serves as an indirect scale. It weighs something that cannot be placed on any physical balance. The region is not perfectly uniform. Some parts may be denser, forming compact clumps. Others may be more diffuse. Winds from the accretion disk can stir the gas, creating outflowing components that add a subtle skewness to the lines. Yet from the distant vantage point used in this story, the details blend into a single calm structure. It appears like a luminous fog wrapped around the central disk, always in motion, but steady in its overall behavior. Within that fog, every cloud follows a path set by gravity and nudged by radiation. The broad line region also marks a transition in the inward journey. Outside, gas still behaves in ways that are only mildly relativistic. Inside it, closer to the disk, orbital speeds approach a significant fraction of the speed of light. The broad line region stands at the edge of these more extreme conditions. That boundary makes it a natural resting place in the narrative, a ring of glowing gas where motion is fast but still understandable, using familiar ideas of orbits and echoes. From here, the next step inward leads to the accretion disk itself, where matter lying even closer to the black hole of S5 0014+81 converts gravitational energy into the intense smooth radiance that powers the entire quasar. Closer to the black hole of S5 0014+81, the flow of gas settles into a broad rotating structure called an accretion disk. An accretion disk is a flattened disk of orbiting gas that gradually spirals inward as it loses energy and angular momentum. The key idea is that this disk turns gravitational energy into light with remarkable efficiency. In the case of S5 0014+81, that process powers a luminosity so high that the quasar outshines entire clusters of ordinary galaxies. Yet the disk itself, when imagined, calmly resembles a layered glowing carousel of matter, circling in patient tight loops. Each ring orbits at a different speed, with inner regions moving faster than outer ones. Friction-like processes between neighbouring layers cause gas to heat, radiate and slowly drift inward. This friction does not mean ordinary rubbing contact, but rather turbulent motions and magnetic stresses in the ionized plasma. Those stresses move angular momentum outward and allow mass to slip inward. As gas falls deeper into the gravitational well, it picks up speed and grows hotter. The energy released in this descent emerges as radiation, especially in ultraviolet and soft X-ray bands. In a gentle picture, each parcel of gas behaves like a small traveller walking down a smooth slope in space-time. With every step, inward part of its stored gravitational energy turns into light. Near the outer disk, the gas may still be relatively cool, shining mostly in optical wavelengths. Closer in, temperatures rise and the radiation hardens. For an ultramassive black hole, the scale is enormous, but the basic pattern remains simple. The disk is thicker than a razor-thin sheet, yet still flatter than a sphere shaped by the balance between gravity pressure and rotation. Vertical motions stir its surface layers, while the midplane holds denser material that carries most of the mass inward. The disk's brightness varies with radius. Inner regions radiate more strongly because they lose more energy per unit mass as they spiral closer to the black hole. Farther out, the gas moves more slowly and releases less energy. When all these zones are added together, the result is a smooth, broad spectrum of light. That spectrum stretches from optical to ultraviolet and beyond, forming the gentle but overwhelming glow that identifies S5 0014+81 as a quasar. The surface of the disk is also not perfectly uniform. Magnetic fields thread the plasma and create small-scale structures, hotspots, and turbulent eddies. These features may cause flickers and fluctuations in the brightness of the quasar on different timescales. From the soft perspective of this narrative, those variations appear as tiny distant shimmers superimposed on a steady shine. The average output remains high and stable over long periods compared to human timescales. In some models, the inner disk around a rapidly spinning black hole extends closer to the event horizon than in a non-spinning case. That difference affects how much energy can be extracted from infalling matter. A spinning black hole allows more efficient energy release, which may help explain the extraordinary luminosity of S5 0014+81. Whether or not the exact spin is known, the concept stays clear. The closer gas can orbit before crossing the final inner boundary, the more gravitational energy it can shed as radiation. The disk, therefore, acts as a quiet engine, whose efficiency depends on both the mass and the rotation of the central object. The emitted light does not simply stream straight outward. Some of it scatters in a hot, tenuous region above the disk, and some reflect from gas further out. However, the disk remains the primary source of the quasar's soft thermal-like glow. It sets the baseline over which harder X-ray components and line emission are layered. For S5 0014+81, The vast scale of the disk means that regions separated by light days or light weeks contribute simultaneously to the observed flux. Small changes near the inner edge can send ripples outward through the radiation field, gently altering conditions in the surrounding broad line region. Over longer periods, changes in the rate of gas supply from the galaxy can modify the disk's structure and brightness. A higher inflow rate thickens the disk and increases its luminosity. A lower rate allows the disk to thin and cool somewhat. Even so, the overall scene remains one of slow adjustment rather than abrupt transformation. The accretion disk quietly responds to what the larger environment provides. This inner structure marks a natural step in the inward journey. Outside it, gas still retains much of its original angular momentum and follows more complex orbits. Inside, the disk orbits become organized and nearly circular, forming a coherent flow that heads toward the last stable paths. From here, the next layer closer to the black hole leads into the hotter, more rarefied corona above the disk, where scattered photons gain extra energy and add a high-energy shimmer to the spectrum of S5014+81. Closer to the innermost regions of the accretion disk around S5014+81, the layered flow of gas enters a hotter and more restless zone. Above and below the disk, a tenuous cloud of energetic particles and radiation forms what astronomers call the corona. A corona in this context is a hot diffuse region of plasma hovering near the disk and black hole. Its main role is to take some of the softer photons from the disk and scatter them to higher energies. In simple terms, the corona adds a high-energy shimmer on top of the smoother glow of the accretion disk. For a quasar as luminous as S5014+81, the corona must handle an enormous flow of power while remaining light in mass. The gas in this region reaches temperatures of many millions of degrees. At such temperatures, electrons move at very high speeds, and magnetic fields become an essential part of the story. Lines of magnetic field rise from the rotating disk and twist together, then sometimes reconnect and release stored energy. That released energy heats the plasma and maintains the extreme conditions in the corona. This behavior resembles the outer atmosphere of a star, but it unfolds on a larger scale and in a deeper gravitational field. Photons that begin their journey in the cooler layers of the accretion disk travel upward into this hot, rarefied zone. When they collide with energetic electrons, they gain energy and move into the X-ray band. The resulting spectrum shows a smooth extension from the disk's ultraviolet light into harder X-rays. It often includes a gentle rollover at the highest energies, where the corona's temperature limits how energetic the photons can become. In the case of S5004+81, this high-energy component carries quiet information about conditions close to the black hole. It reveals how hot the corona is, how dense it might be, and how strongly it couples to the disk below. Some of the X-rays that leave the corona travel straight outward into intergalactic space. Others shine back down onto the disk where they are absorbed, scattered, and re-emitted. This back and forth of radiation creates a soft echo in the spectrum, including features that show the presence of heavy elements in the disk. Those echoes carry imprints of both the disk's motion and the space-time geometry near the black hole. For an ultramassive object like the one in S5014+81, relativistic effects become strong close to the inner edge of the disk. Gravitational redshift and Doppler shifts smear and skew the reflected features, turning them into gentle traces of the deep potential well. From a calm narrative viewpoint, the corona appears as a faint hot halo clinging to the disk, glowing most strongly in invisible penetrating light. It flickers in response to changes in the accretion flow, sometimes brightening, sometimes dimming, yet always linked to the broader structure below. Small variations in the rate at which matter reaches the inner disk can change the balance between disk emission and coronal power. Over human timescales, these variations may appear as subtle shifts in the spectrum, small changes in hardness that hint at evolving conditions near the event horizon. The corona also plays a quiet role in shaping any jets that may emerge from the inner region. Magnetic fields that support the corona can help collimate and launch narrow beams of plasma along the rotation axis. In this way, the high-energy environment above the disk becomes a strong source of X-rays. It also serves as a staging ground for more extended structures. Even if the details remain uncertain, the broad picture is simple. Rotation magnetic fields and hot plasma combine to form a complex but ordered inner environment. S50+81 represents an extreme realization of this environment and scales it up to enormous size. The mass of the black hole expands the inner disk while the immense luminosity pushes the corona toward very high power output. Yet the same basic principles apply as in more modest systems. Gas falls inward, magnetic fields rise and reconnect, photons scatter, and a characteristic high-energy tail appears in the spectrum. Seen over cosmic time, this inner halo may brighten and fade many times without disturbing the wider structure around it. Each phase leaves a quiet imprint on surrounding gas, gently adjusting how later generations of matter reach the disk. The corona therefore serves as a bridge between the thermal emission of the disk and the extended phenomena that carry energy outward. Within the flow of this story, it marks a quiet turning point. Inside this zone, structures shift from mainly converting gravitational energy into light to launching energy back into space. With the corona in place above the disk of S5, attention can now follow the outward path of energy. Some of the energy escapes as narrow relativistic jets that reach far beyond the host galaxy. Closer to the spin axis of the black hole in S5014+81, energy leaves the inner regions in narrow extended beams called jets. A jet in this setting is a focused outflow of particles and fields launched from the vicinity of the accretion disk and black hole. The central idea is that these jets act as long, thin bridges carrying power from a tiny region out into intergalactic space. Instead of light alone, they transport matter and magnetic structure along almost straight paths for vast distances. Near their base, the jets remain tightly connected to the accretion flow and corona. Rotating plasma and twisted magnetic fields combine to extract energy from the inner disk, and possibly from the spin of the black hole itself. The exact details remain uncertain, but the broad picture stays calm and ordered. Magnetic field lines anchored in the disk can wind up like coiled springs. When they unwind, they push material outward along the rotation axis, forming twin streams that leave the system in opposite directions. In a gentle mental image, the central engine of S5, 0014+81, is surrounded by two faint elongated beams, one above the disk and one below. These beams are not solid objects. They are flows of charged particles moving at speeds close to the speed of light. As they travel, they emit radiation, especially at radio and high-energy wavelengths. The result is that the quasar does not shine only from its center. It also glows along these extended lines, turning the region around the galaxy into a softly illuminated corridor. For a source as bright as S5014+81, the jets likely reach far beyond the visible extent of the host galaxy. They can pierce the surrounding circumgalactic medium and continue into the sparse intergalactic gas. Along the way, they inflate large low-density lobes where energy collects, These lobes act as gentle cushions, pressing back on the surrounding medium and slowing the inflow of fresh gas. In this way, the jets contribute to feedback the process by which a central black hole influences the growth of its host and its environment. The important point is that the influence is broad and extended even though the engine is small compared with the galaxy. Over millions of years, the jets can heat gas far from the center. Heated gas resist collapse and stay suspended, which can reduce the rate of new star formation. At the same time, shocks driven by the jets may compress some regions, perhaps encouraging local bursts of star formation. The overall effect is a balance between stirring and support, between gentle suppression and occasional stimulation. For S5 0014+81, the enormous power of the central engine suggests that its jets, when active, have a strong role in setting conditions throughout the halo. The jets also offer a clear signpost for observers. Radio maps reveal elongated structures that mark the jet paths and the inflated lobes at their ends. X-ray observations sometimes show bright knots, where the jets encounter denser clumps of gas. Each knot is a place where energy changes form from ordered motion into heat and radiation. Even if the fine structure is complex, the story can be held in a simple picture. The black hole and disk send out narrow streams that act as long arms touching the medium on scales much larger than the galaxy itself. Over very long times, the direction of the jets may drift as the spin axis of the black hole changes, or as the accretion flow tilts. Such changes carve multiple channels in the surrounding gas, leaving behind a softly layered record of past activity. Some cavities may refill slowly with cooler material. Others may remain hot for an extended period. Together they form a patchwork of regions where gas is more or less ready to fall inward again. This patchwork matters because it regulates how much fuel can return to the central regions and at what pace. Jets' lobes and the surrounding medium participate in a quiet conversation that spans vast distances. Energy flows outward along the beams. Matter and radiation respond by changing the temperature and density structure of the halo. The central black hole in turn receives the long-term consequences of its own past output as new inflows arrive along reshaped paths. For a listener following this story, the essential idea is that jets are not violent intruders in an otherwise passive setting. They are part of a long, slow feedback loop. That loop links the smallest scales near the event horizon to the broader scales of the halo and cosmic web. With the role of jets and feedback sketched in this gentle way, the narrative can move inward once more. It turns toward the innermost orbits where matter circles on the last stable paths before reaching the very edge of the black hole's domain. Very near the core of S5 0014+81, the calm curves of the accretion disk approach a special boundary in space-time called the innermost stable circular orbit. The innermost stable circular orbit, often shortened to ISCO, is the smallest distance from a black hole where circular motion remains stable. Inside this orbit, no circular path can persist without quickly plunging inward. The central idea is simple and quietly powerful. The ISCO marks the last safe ring where gas can circle the black hole for many orbits before falling in. Everything inside that ring lies on borrowed time. For a black hole as massive as the one in S5 0014+81, the ISCO sits far from the horizon in absolute kilometers, yet still very close in terms of gravitational radii. In this region, orbital speeds reach a significant fraction of the speed of light. Space and time are strongly curved and familiar intuitions from gentle gravity begin to bend. Even so, the flow of matter keeps a clear structure. Just outside, the ISCO gas in the disk follows nearly circular paths radiating away energy and slowly spiraling inward. As it approaches the critical radius, the shape of space-time changes the balance of forces. Small disturbances that a little farther out would simply produce gentle oscillations here lead to rapid inward drift. The result is that the disk develops a quiet transition zone. In that zone, the radial inflow speeds up, and the pattern of motion becomes less like a long-lived orbit and more like a smooth descent. The temperature and density also adjust since matter has less time to cool radiatively before moving deeper into the gravitational well. For an observer at a great distance, the region near the ISCO contributes strongly to the inner, hotter part of the disk spectrum. The energy released per unit mass increases toward this radius and then drops as matter passes inside and radiates less efficiently. In a soft mental image, the ISCO appears as an invisible ring drawn on the luminous disk. No physical mark is present in the plasma, yet the flow changes character as it crosses this gentle boundary. Outside, the ring orbits are stable and long-lived. Inside, paths curl rapidly inward and end at the horizon. The position of the ISCO depends on the spin of the black hole. For a non-spinning black hole, it sits at a larger radius. For a rapidly spinning one, the orbit can move closer in, especially for gas that orbits in the same direction as the spin. For S5-0014+81, the exact spin remains uncertain, but the quasar's high luminosity suggests that efficient accretion may bring the ISCO relatively close to the horizon. A closer ISCO means more gravitational energy is available to convert into light before matter plunges in. This subtle shift affects the overall efficiency of the disk and helps set how much power the quasar can radiate for a given mass inflow rate. In addition to its role in energy release, the ISCO influences how the inner disk looks when its light is distorted by relativistic effects. Material orbiting close to this radius experiences strong Doppler boosting and gravitational redshift. Parts of the inner disk that move toward the observer appear slightly brighter and bluer. Parts moving away appear dimmer and redder. These contrasts smeared by light, bending create a soft pattern in the disk's emission. The line profiles from elements in the inner disk become broadened and skewed, offering indirect evidence of motion near the ISCO. For an ultramassive system like S5-0014+81, these signatures exist on scales far beyond any direct imaging, yet they still leave quiet traces in the spectrum. In the inward flow, the ISCO also marks a division between two phases of the gas's journey. Before reaching it, matter can linger orbiting many times while gradually losing angular momentum. After passing it, motion becomes almost free fall, guided more by the geometry of space-time than by local friction processes. The plunge region inside the ISCO is therefore thinner in terms of radiation output. Most of the light has already been released before crossing this threshold. The remaining descent adds less to the quasar's brilliance, but remains essential for the black hole's growth. Each parcel of gas that crosses the ISCO carries the final mass that the black hole gains. Over cosmic time, countless such parcels contribute to building the tens of billions of solar masses at the core of S5-0014+81. The ISCO can thus be imagined as a quiet gate in space-time. It does not resist the flow, yet marks the point beyond which return is no longer possible. Outside the gate, matter can, in principle, exchange energy and angular momentum, and even move outward again. Inside, all paths curve inexorably toward the horizon. This simple boundary helps make sense of an otherwise abstract gravitational landscape. Within the smooth motion of the disk, it provides a natural marker that separates stable rotation from terminal infall. With the concept of the innermost stable orbit gently in place, the journey can move one step closer to the black hole. Just outside the event horizon lies another curious layer where light itself can circle in tight loops. That layer, known as the photon sphere, shapes the paths that photons follow and adds a new twist to the view of S5-0014+81. Just inside the region of last stable orbits around the black hole of S50014+81 lies a stranger layer where light itself can circle. In this zone, the gravitational field is strong enough that photons can move on nearly closed paths. The simple idea is that gravity bends light so sharply here that a beam can loop partway or fully around the black hole before escaping or falling inward. This special layer is called the photon sphere. The photon sphere is the region where light can follow circular or nearly circular tracks. Unlike the orbits of gas in the accretion disk, these paths are unstable. A tiny outward nudge sends the photon away to infinity. A tiny inward nudge sends it toward the horizon. Because of this instability, the photon sphere behaves less like a solid ring and more like a thin, delicate band, where light hesitates before choosing a direction. For a listener picturing the scene, it can be imagined as a fragile glass ring in space-time, almost invisible yet important. Photons that skim this band may loop around the black hole many times, weaving intricate paths before escaping. Others cross the region only once, but still bend sharply. From far away, these complex routes produce a subtle but powerful effect. Light from the inner disk and hot plasma can pile up near certain angles, enhancing brightness in a thin halo around the projected shadow of the black hole. If it could be resolved in detail, the central region of S5 as 14+81 would show a dark interior encircled by a narrow, bright ring. That ring is not a physical structure like the accretion disk. It is a pattern created by the way space-time bends the paths of photons near the photon sphere. The photon sphere therefore marks a transition in how light behaves. Farther out, gravitational lensing gently bends rays and slightly distorts background images. Closer in near this layer, bending becomes extreme. Light can be turned back toward the observer from directions that would normally remain hidden. Photons from the far side of the disk, for example, can curve around and appear in front. This wrapping of light means that multiple images of the same region can overlap. Each image arrives with a different degree of bending and a different delay. In a calm mental picture, the inner environment of S50014+81 is surrounded by a thin halo, where light has been folded and refolded by gravity. This halo helps define the apparent size and shape of the black hole's shadow. Even though current instruments cannot resolve such detail at the distance of this quasar, the underlying physics remains the same as in closer systems. The photon sphere communicates how strongly space-time is curved and sets the scale of the central silhouette. For an ultramassive black hole, the physical radius of this layer is vast, reaching hundreds of billions of kilometers, yet from the point of view of space-time geometry it sits only slightly outside the event horizon when measured in gravitational radii. That closeness means photons here experience both extreme time dilation and strong gravitational redshift. Their clocks run slower compared with clocks far away. Their wavelengths stretch as they climb out of the deep potential well. By the time such photons reach distant detectors, their colors and arrival times carry these quiet distortions. The photon sphere also influences how variability in the inner disk appears. Light emitted from different radii and different sides of the disk follows different kinds of curved paths. Some rays reach the observer directly. Others loop near the photon sphere before emerging. The result is a gentle smearing of rapid changes and the possibility of subtle echoes in the light curve. In practice, these echoes are difficult to separate from other processes, but they form part of the complete layered story. The presence of a photon sphere underscores a central lesson. Near S50014+81, gravity does not simply pull more strongly. It changes the geometry through which every particle and every photon must move. Straight lines in this region are no longer straight in any ordinary sense. They are geodesics in a curved space-time, and near the photon sphere these geodesics can loop back on themselves. Light that seems to hover on the edge of falling traces out the most delicate of these paths. Just inside this slender layer, the paths of photons no longer find long-lived orbits. They dive inward toward the horizon, or escape outward with less chance of looping. The photon sphere therefore stands as another quiet boundary, marking where light can briefly circle, and where it must choose between return and disappearance. With this structure in mind, the story can take its final inward step. Beyond the photon sphere lies the event horizon of the black hole in S0014+81. Not a solid surface, but a boundary in spacetime that separates the visible universe from regions that no signal can leave. From the photon sphere around the black hole of S50014+81, the next inward step leads to the event horizon itself. An event horizon is a boundary in spacetime beyond which no signal can return to distant regions. It is not a solid surface, not a wall one could touch, but a one-way edge defined by the paths that light and matter can follow. The essential idea is calm and exact. Outside the horizon, paths can still curve back outward under the right conditions. Inside, every possible path bends inward toward the center. For a black hole with tens of billions of solar masses, the event horizon spans a diameter so large that light would need days to cross it. In absolute scale, it rivals the size of a planetary system, yet in the language of gravity it still sits only a short distance from the photon sphere measured in gravitational radii. Near this boundary, time and space trade rolls in a subtle way. To a distant observer, clocks close to the horizon seem to slow. Signals from matter plunging inward arrive more and more redshifted and delayed. The infalling material appears to hover, fading and stretching as it approaches the edge. From the viewpoint of the matter itself, though, the crossing happens in a finite proper time. This contrast between inner and outer perspectives is one of the quiet wonders of black hole physics. The horizon marks a division not only in space but in experience. Outside events can still influence the wider universe. Inside, they become part of a region that cannot send information outward again. For S50014+81, the event horizon therefore acts as a calm final gate in the inward story of gas. Every parcel of matter that passes this gate contributes permanently to the mass and spin of the black hole. Its detailed structure disappears from view, leaving only its energy and angular momentum as part of the black hole's simple description. Around the horizon, gravitational lensing reaches its most dramatic form. Light from the accretion disk corona and broad-line region can be bent through large angles. Some rays skim close to the horizon and then return outward, carrying with them an imprint of the deep gravitational well. Others cross the horizon and are lost. Those that escape contribute to the complex pattern of brightness in the immediate surroundings. If the central engine of S50014+81 could be resolved with extreme clarity, the horizon and its lensed environment would create a distinctive silhouette. A dark interior representing the shadow of the black hole would sit surrounded by a bright ring influenced by the photon sphere. Around that would glow the inner parts of the accretion disk, distorted by Doppler boosting and gravitational redshift. At the great distance of this quasar, no current instrument can see such detail, yet the underlying structure still shapes the light that finally arrives. Gravitational lensing does not end near the horizon. On larger scales, the combined mass of the black hole, its host galaxy and surrounding halo, can bend and magnify the light from background sources. In some configurations, this bending creates arcs or multiple images of galaxies lying even farther away. S5 0014+81 sits both as a lens for more distant light and as a lensed source in its own right, because the matter between it and Earth also bends its radiation. The journey of each photon from the quasar to the telescope passes through a chain of curved regions in space-time. Over billions of years, the universe expands while that photon travels. Its wavelength stretches, its energy decreases, and its color shifts toward the red. This cosmological redshift combines with the gravitational redshift imprinted near the horizon and the Doppler shifts from orbital motion. By the time the photon is detected, it carries a layered record of motion, gravity, and expansion. Time dilation also shapes how variability in the central engine appears. Rapid changes near the horizon are slowed and smoothed for distant observers. Even if the innermost flows evolve quickly, their signals reach Earth stretched across longer intervals. As a result, the quasar's brightness fluctuations unfold at a restful pace on human timescales. Subtle rises and falls in luminosity trace slow patterns rather than abrupt jumps. This smoothing adds to the tranquil impression created by the enormous distance. From the vantage point of the present universe, S5, 0014+81 appears as a single steady beacon in Cepheus. Its intricate inner structure from cosmic web to event horizon condenses into one bright point in the sky. The black hole's horizon, though vast, occupies no visible area on the detector. Its influence is felt only through the energy it allows to leave before matter crosses the edge. With the role of the event horizon and its time-warped, lensed environment now quietly in place, the narrative is ready for a final step outward. The next view will return to the large-scale universe and consider how S5 0014+81 with its ultramassive black hole fits into the broader limits of observation and understanding. On the sky of the present universe, S5 0014+81 appears as a single bright point in the quiet constellation of Cepheus, yet behind that point lies the layered structure traced through this journey. The central idea now is that even the most extreme black hole remains part of a wider pattern and sits within clear limits of observation and understanding. Light from the quasar carries rich information, but it does not reveal everything. Some regions are hidden behind dust, some lie beyond current instrumental resolution, and some fall inside the event horizon where no signal returns. These limits simply mark the edge of what present methods can reach. S5 0014+81 stands as a calm reminder that knowledge grows within boundaries that move slowly outward with each new generation of telescopes and theories. Their steady bright light acts as a backlight for faint gas in the cosmic web, a probe of chemical enrichment in early galaxies, and a marker of how fast black holes can grow. Its ultramassive black hole and intense luminosity provide a strong test for models of black hole seed formation, accretion physics, and galaxy evolution. If such an object can exist when the universe is still young, then gas must have been able to flow inward efficiently along filaments through halos and intergalactic cores. The pathways described earlier become more than abstract diagrams. They turn into necessary ingredients in a quiet explanation of how this quasar came to be. At the same time, the extremeness of S5 0014+81 shows where current ideas feel stretched. Some scenarios imagine heavy seeds forming from dense collapsing gas clouds without first passing through an ordinary stellar phase. Others rely on long periods of rapid, nearly continuous accretion that push against limits set by radiation pressure. Observations so far do not single out one option with certainty. Instead, they trace a narrow corridor of possibilities that remain open. Within that corridor, S5 0014+81 acts as a boundary marker for theory. any successful picture of early black hole growth must leave room in its map for a quasar of this scale. Yet the quasar also reassures by staying remote and stable on human timescales. Its great distance and age mean that its brightest phases began long before Earth formed. Its tremendous gravity does not threaten local space. It simply adds another calm point to the tapestry of the distant sky. In this way, the object is both astonishing and harmless, both a dramatic expression of gravity and a quiet background detail in the nightly view. The limits of observation around S5 0014+81 are equally layered. Instrumental sensitivity restricts what can be seen of its host galaxy and environment. Resolution limits blur the inner structure into a single unresolved core. Even at the most detailed level, general relativity sets a final limit at the event horizon, beyond which no measurement can report back. Between these outer and inner boundaries lies the domain where data and theory still meet. Spectra reveal broad and narrow lines. Light curves show slow variations. Models of accretion disks coronas, and jets translate these signals into a consistent, if incomplete, picture. In that picture, the quasar does not stand alone. It connects to less extreme active galaxies nearby to fainter quasars at similar redshifts, and to the quiet black holes at the centers of present-day galaxies. Together they outline a long story in which black holes and galaxies grow side by side. S500+81 occupies a bright, early chapter of that story. Seen in this light, the ultramassive black hole no longer appears as an isolated monster swallowing billions of suns. It becomes one endpoint on a smooth curve of mass and luminosity. On that curve, each system reflects the balance between gas supply, gravitational depth, and feedback into its surroundings. Gravity organizes matter across many scales, from the thin filaments of the cosmic web down to the last stable orbits near a horizon. Radiation winds and jets carry information and energy back outward, closing loops that reach from the heart of a quasar to the edge of its halo and beyond. For S50014+81, those loops have been running quietly for most of cosmic history. The light seen today is one moment in that long sequence. It passes through the expanding universe, through foreground structures, and finally into instruments on a small world. From the perspective of the story told here, this light also closes a conceptual loop. The narrative has moved from the larger scales of structure down to the event horizon and back out again to the distant sky. Along the way, each layer has offered a calm reason to be curious and a clear sense of why it matters. The journey ends not with a sharp mystery, but with a gentle pause at the limits of current knowledge. Beyond those limits, new observations and ideas will gradually extend the map. For now, S50014+81 can rest in the mind as a distant, steady landmark in Cepheus, holding an ultramassive black hole that remains safely remote while quietly illuminating the structure and history of the universe. In the far distance, S50014+81 continues to shine as a steady point in Cepheus, carrying in its light the whole layered structure just explored. The ultramassive black hole at its center keeps rotating in silence, wrapped in its disk corona and gently glowing halo of gas. Around it, the host galaxy orbits within its dark matter halo, and the wider cosmic web continues to feed and guide the region without haste. Every part of this system follows clear physical rules, even when the scales feel almost beyond imagining. That quiet order is one of the most reassuring aspects of the picture. Gravity, radiation, and time work together in ways that remain consistent, from small systems up to giants like S50014+81. On human scales, the quasar stays frozen in a single patch of sky, changing only slowly over spans far longer than a lifetime. Its great distance keeps it safely remote, turning it into a calm lantern of the early universe, rather than any source of concern. The light that arrives now began its journey when the universe was young, and has crossed billions of years without losing the simple information that gravity can shape matter into disks, jets, and halos. Even the event horizon with all its mystery appears as a clean boundary in that shared framework instead of a threat. Seen this way, the quasar becomes a distant marker of how far understanding has already reached. It shows that known physics can describe environments from the outskirts of a halo down to the last stable orbits around a black hole. Beyond that, it gently marks where current knowledge ends and new observations will be needed. For now, S-file 0014+81 can rest in thought as a quiet, luminous landmark holding its ultramassive black hole in deep cosmic night, while the universe around it continues to expand and cool at an unhurried pace.